Continuing section 4.5, we'll now talk about concavity and points of inflection. We can use the mean value theorem to determine where a function is increasing or decreasing, but there's another issue to consider regarding the shape of a graph for a function. If the graph curves, is it curving upward or is it curving downward? So if you can imagine a curve going upward or a curve going downward. This idea is called concavity. We have the definition of concavity here. So f could be a function that's differentiable on an open interval if the derivative is increasing on the entire interval. We say that the function is concave up. If the derivative is decreasing, then we would say it's concave down. So we have a couple of images here that I want to point out. Each one of these graphs shows a tangent line on top of a function. So for part A, we have a tangent line here and we have a tangent line here. We can see that the derivative is getting larger as we move down the number line. So maybe this first tangent line has a slope of 1/2. Maybe the second tangent line has a slope of 4. So the derivative got larger. The derivative is increasing. In the second picture, in picture B, we have a derivative here, a tangent line, and another one here. And in this case, it looks like maybe the first slope is like 4, and maybe the second slope is about 1/2. In this case, the derivative got smaller as we moved down the number line, and that's what we mean by the derivative is decreasing. So if you compare derivative values along the number line, if the numbers are going up, then we would call the function concave up. If the numbers were going down, we'd call the function concave down. Theorem 410 gives us a test for concavity. If we're looking at how the derivative is changing, is the derivative increasing? Is the derivative decreasing? Essentially, we're applying the mean value theorem to the first derivative, which means take the derivative of the first derivative or use the second derivative. We're going to look at the sign of the second derivative. If the second derivative is positive, then we're looking at concave up. I like to use a double plus to say second derivative is positive with a concave up smile face. And for the second part of this theorem, if the second derivative was negative, I'll do two negatives side by side, then we'd say that's concave down. So I use these two faces to help me determine if we are looking at concave up or concave down. Positive derivative, concave up, negative derivative, concave down. And that's referring to the second derivative, to be clear. So now we can use these derivatives to identify where the function is increasing, decreasing, or concave up, concave down. So taking a look at the image we have here on the screen, we can see the second derivative is positive for the entire portion of the curve that looks like it could hold water. So if I poured water on this function, this concave up section could hold the water. And then we hit something called an inflection point. This essentially is that critical point that we keep finding that doesn't give us a max or a min. This inflection point is what switches us from a concave up function to a concave down function. To the right of that inflection point, the second derivative is negative, meaning we're concave down. Oops. So for our definition of an inflection point, it's basically the point where the concavity changes, where you go from concave up to concave down, or from concave down to concave up. To test for concavity, we're going to find the second derivative and then look at if it's positive or negative. So starting with our first derivative of f, we have f prime would be 3x squared minus 12x plus 9. but we need the second derivative here, so we're going to take the derivative of that to get 6x minus 12. To find any inflection points, we need to check to see where the second derivative changes sign. So inflection points occur when the second derivative is equal to 0. In other words, we're going to take that 6x minus 12, set it equal to 0, and solve to find x equals 2. So we will have an inflection point at x equals 2. I'm going to put that on our number line because that is the place where our function changes concavity. So it's either concave up on the left and concave down on the right, or it's concave down on the left, concave up on the right. To figure out what we have, we're going to look at the second derivative at some test points, just like we did before. So let's pick a test point. To the left of 2, I'm going to pick 0. So I'll plug that into my second derivative. And to the right of 2, I'll pick 3. So we'll plug 3 into our second derivative. And again, we don't care what the value of the second derivative is. We just care if it's going to be positive or negative. Plugging 0 into our second derivative, we get 6 times 0 minus 12, or negative 12. Therefore, we have a second derivative that is, second derivative at 0 is negative, which means we are in the case with concave down. And when we test our second derivative at positive 3, we get 6 times 3 minus 12, or 18 minus 12, which gives us a positive 6. So our second derivative at 3 is positive, meaning we have concave up. So the question says to determine the intervals where f is concave up. We see that it's concave up to the left of positive 2. To write that as an interval, we would say everything to the left of 2 is negative infinity all the way up to 2. And then our concave up interval starts at 2 and continues to the right. Man, I have that backwards. Left of 2 is concave down. Right of 2 is concave up. The concave up interval would then say from positive 2 up to positive infinity. And then it says to list the inflection point, so let's go ahead and list that. That happens at x equals 2, and then we could plug 2 into our original function to find the y value of that critical point. So we would have 2 cubed minus 6 times 2 squared plus 9 times 2 plus 30 to get 32. So our inflection point is at 232. And it says to use a graphing utility to confirm your results. So let's switch over to Desmos. To confirm our results, we're going to graph the original function, which was x cubed minus 6x squared plus 9x plus 30. And there's some stuff going on that we can't see, so let's reset our graph, zoom out, and then find where the interesting stuff is going on, zoom into that. We found that the function was concave up to the left of that inflection point that we found at 2. Let's go ahead and graph our inflection point. 2, oh, I didn't define my function up here. I can't call to f if I haven't said that this is f of x. Okay, so now when I graph my point, I can say 2 comma f of 2. Places me right there at 2 comma 32, just like we said. To the left of that point, the function is concave down. To the right of that point, the function is concave up.